Okay, we ended the last video talking about stretching, and I'd like to say just a few more things about that. I don't know that I've made it very clear, so let's draw a rectangle here. Now let's just say it has a base B and a height h, and we know that the area equals base times height. And so now I want to stretch this thing. Let's stretch it out here. I'll say that that is going to be a length of 2 times the base. That is, I stretch it out by a factor of 2 horizontally. And not drawn to scale here, but let's say this is I stretched vertically the height h by a factor of 3, so that is 3h. So we look at the new area here, and this new area is clearly going to be 2 times the base times height plus 3 times h. And so that area equals 3 times 2 times base times height. And you notice here that it is the original area, base times height, and then times the factors that we stretched by. I stretched horizontally by 2, and I stretched vertically by 3. Okay, and that's going to give us that our new area equals 6 base times height. But more importantly, what we're really getting at here is when we stretch something, when we're given an area and we stretch it by vertically by some factor, or horizontally by some factor, and vertically by some factor, the new area, so if we have an area A and we stretch vertically by 5, stretch horizontally by 10, the new area is going to be 5 times 10 times the original area. Okay? And where this becomes useful is in the fact that, say, given a circle, we can really break the circle up into little rectangles, and this is really getting into the idea of calculus, breaking curved surfaces into rectangular surfaces that we can feel more comfortable dealing with, and you do that for the rest of the circle. And so if you stretch that circle horizontally by a factor of r, so stretch horizontally by some factor of r and stretch vertically by some factor of r, what you're really doing is stretching those rectangles. And so we go back to this argument, we'd say that the new area would be the old area A times r squared. Okay? So we're going to use that idea over here to try to get the area of a circle. So first let me draw a unit circle. That's going to be a circle of radius 1. And now let's do a little bigger circle. It's going to be a circle of radius r. So that is, it's going to be radius 1. And now I'm going to stretch it. I'm going to stretch it vertically by r. So length r times 1 is r. And I stretch horizontally by r. So we still have a circle of radius r. And we're going to say that if we call, let's say the area of the circle of radius 1, let me draw that with the color there. Say area equals P. Then the new area of the big circle, I'm going to call that one, it says area B, equals P, the original area. I stretched it horizontally by a factor of r, and I stretched it vertically by a factor of r, so PR squared. Okay? And now what we know what we really want to do is show that that P is actually pi. So here's how it goes. So we look at this area between the two circles here. And what we want to imagine is actually splitting this thing right there and laying it out. And what that's going to do is it's going to create a trapezoid where that side is going to be the circumference of the big circle, okay, which is 2 pi r, and we got that in the couple videos ago. And then we're going to have this side is going to be the circumference of the smaller circle, which is 2 pi. Okay, and note that it's this side is shorter than the bigger side, and so it leaves us with a trapezoid here. And so all we need to know is the height of the trapezoid. And the height of the trapezoid is going to be given by, if this is a length 1 and then this is a length r, then what's left here is going to be r minus 1. And so we're going to get that the area of that trapezoid, I'm going to call that AT, equals 1/2 times 2 pi plus 2 pi r times r minus 1. Okay, and doing a little algebra here, factoring out the 2 pi. Note that the 2's with the 1/2 will cancel each other, and it leaves me with pi times r plus 1. That's r plus, and that's going to leave me with a 1 times r minus 1. And so the area of the trapezoid equals pi times, do your distributive property here, and you're going to get r squared minus 1. A minus b times a plus b is a squared minus b squared. Okay, so the area of that trapezoid is 1. So we get that the area of the big circle equals the area of the smaller circle, which is p, plus the area of the trapezoid, which equals pi times r squared minus 1. Okay? But we know up here that the area of the big circle is pr squared. Pr squared equals pi plus pi times r squared minus 1. Bring the p over, subtract p from both sides, and get p r squared minus p equals pi times r squared minus 1. And factor out the p and get p times r squared minus 1 equals pi times r squared minus 1. Well, something times r squared minus 1 equals something times r squared minus 1. Those two things must be equal. Therefore, p equals pi. And then up here, that's going to give us that the area of a circle of radius r equals pi r squared. Okay, now I know that's not simple. Most of you already knew that the area of a circle is pi r squared, but this starts to give us an idea of why it's true. And when you get into calculus 2, you'll prove it with even a better method, that the area of the circle equals pi r squared. Okay, and you want to go back and watch this video. For those of you who truly want to understand this, go back and watch the video, slow down, read it in the book, write it down yourself, watch the video, read it in the book, write it down yourself. It might take a few times. Note that math is, sometimes reading math is not like reading a novel. You can't just skip parts you don't like. Okay, you have to read every single line, and every single line has to make sense. All right, happy reading.